Continuing on with our discussion on wave motion, let's have a few more examples. Okay, so let's have sample problem number 4. Consider the following problem. The resonant oscillation of a string of mass 2.5 grams and length 0.8 meters has 4 half waves and an amplitude of 4 millimeters. The string is under tension 325 newtons. Determine the harmonic number, wavelength, and frequency of the oscillation of the standing wave. Resonant oscillation basically means standing wave formation. So this is standing wave in a string. So determine the harmonic number, wavelength, and frequency of the standing wave in a string. Likewise, determine the maximum transverse velocity of the string. Maximum transverse velocity, we are being asked to get the maximum particle velocity of the string. So we have mass of the string, 2.5 grams, convert to kilograms. Let that be mass M. Length of the string is given, 0.8 meters. Let that be length L, 0.8 meters. The amplitude of the oscillation is given, amplitude of 4 millimeters. This is resonant oscillation. Standing wave formation. This is amplitude of a standing wave. So YSW is equal to 4 millimeters. Convert to meters. And the tension is of the string the tension of the string is given 325 newtons. Let that be force F. We are looking for harmonic number N, wavelength lambda, and frequency F. Likewise, we are looking for maximum particle velocity, Vy max. Now, the problem tells us that the standing wave has 4 half waves. In standing wave formation, one segment is 1 half wave. So if there are 4 half waves, that means there are 4 segments. And for 4 segments, the harmonic number is 4. N is equal to 4.000. Now, for standing wave in a string, we know the equation for the wavelength. Lambda n is equal to 2L over n. And n is equal to 4, so lambda n is lambda 4. That will give you 2L over 4. And knowing L, 0.8 meters, we are able to determine lambda 4. Lambda 4 is equal to 0.400 meters. And for standing wave in a string, the harmonic frequencies, the harmonics is given by Fn is equal to n over 2L square root of f over mu. N over 2L times square root of f over mu. Mu is linear mass density. It's just equal to mass of the string divided by length of the string. Completo. We know the harmonic number and we know L. And lastly, we know the tension in the string. We are able to determine the frequency. N is equal to 4, so frequency is F4, fourth harmonic frequency. Plot in the known values, we are able to calculate the frequency to be 806.226 Hertz. So we have a standing wave, resonant oscillation, in particular, standing wave in a string. Using the wave function for a standing wave, we are able to determine the maximum particle velocity. Wave function is basically the position function for a standing wave. The standing wave function is given by YSW sine kx cosine omega t, getting the differentiation of y with respect to t. You have dy over dt. That will give you Vy, the particle velocity function. The velocity function is given by negative omega YSW sine kx sine omega t. And the maximum value of this function is just the amplitude, omega YSW. So you have Vy max is equal to omega YSW. Omega, angular frequency, is just 2 pi frequency. And the frequency that we have is F4. So 2 pi F4 YSW. Plotting in the values, we are able to determine the maximum particle velocity. The maximum transverse velocity, Vy max, is equal to 20.263 meters per second. And we have sample problem number 5. Two sinusoidal waves with identical wavelengths and amplitudes travel in opposite direction along a string with a speed of 15 centimeters per second. This is exactly the condition for standing wave formation. A one-segment standing wave is produced. If the time interval between instants when the string is flat is 0.2 seconds, what is the wavelength of the waves? Determine the fourth overtone. So the speed of the wave speed is given 15 centimeters per second. Let that be speed V. Convert to meters per second. A one-segment standing wave is produced. One segment, n is equal to 1. Time is given, 0.2 seconds. Time interval between instants when the string is flat. Let that be time t. T is equal to 0.2 seconds. We are being asked to get the wavelength of the waves. Since the two waves are identical, there's only one wavelength. This is also basically the wavelength of the standing wave. Standing wave with one segment. So lambda 1 we are looking for. Determine the fourth overtone. Fourth overtone is F5 for standing wave in a string. Now, the time given, time interval between instants when the string is flat, this is basically time for half a wave, which means the period which is time for one wave is just twice the given time. So T1, because n is equal to 1, so period for standing wave with one segment, T1 is equal to twice the time provided, 2 times 0.2 seconds. T1, the period, is given by 0.4 seconds. And the inverse of the period is frequency. You have T1, so F1 is equal to 1 over T1, which will give us 2.5 Hertz. F1 is equal to 2.5 Hertz. And knowing the speed of the wave and knowing the frequency of the wave, we are able to determine the wavelength of the wave. This is still a periodic wave. For a periodic wave, V is equal to F lambda. You have F1, so F1 times lambda 1. Lambda 1, therefore, is just V over F1. We're able to determine the wavelength. lambda 1 is equal to 0.060 meters. And knowing F1, we are able to determine the fourth overtone, F5, because one equation for the harmonic frequencies is Fn is equal to Nf1. Fourth overtone is F5. Harmonic number is 5. So F5 is equal to 5F1. 5F1 or F5 will give you 12.5 Hertz. F5 is equal to 12.500 Hertz. Lastly, we have sample problem number 6. Standing waves are produced in a pipe that is 45 centimeters long. If the pipe is closed at one end, what is the number of the highest harmonic that may be heard by the average person? The highest frequency that may be heard by the average person is given by 20,000 Hertz or 20 kilohertz. Use speed of sound equal to 344 meters per second. So length L of the pipe is 45 centimeters. Convert to meters. The highest frequency that may be heard by the average person is 20,000 Hertz. The speed of sound to be used is given 344 meters per second. We are looking for the number of the highest harmonic frequency. So that means we are looking for the highest harmonic number that will give us the highest frequency that may be heard by the average person. So we are looking for N highest. Now this is pipe closed at one end. You have stopped pipe case. The harmonic frequency for stopped pipe case we know to be Fn is equal to Nv over 4L. Let's set Fn to the highest frequency that may be heard by the average person. So Fn is equal to F highest. Isolating N, we get the harmonic number that will give us the highest frequency that may be heard by the average person. So plotting in the values, we are able to determine that N is equal to 104.6511628. The harmonic number that will give us F highest. Now for stopped pipe case, pipe closed at one end, you have odd harmonics, meaning N is equal to 1, 3, 5, 7, and so on. Odd integers greater than 0. Odd number, that means the N that we calculated, N is equal to 104.6511628. This is not allowed because the allowed harmonic number for odd harmonics should be odd number. The nearest odd numbers for this value of N is either 103 or 105. So N will either be 103 or 105. Odd harmonic number. Now, which one is it? 103 or 105? If we use 105, N is equal to 105. If we use that into this equation, we will get a frequency that is greater than 20,000 Hertz. Meaning, F105 is no longer heard by the average person. That means n is equal to 103. So n is equal to 103.000. And that's it for now. That's it for our discussion on examples part 2. We'll continue our discussion in the next video. In the next video, we'll cover the concept of sound intensity. So again, that's it for now, and thank you for watching.